Hi. Okay, I don't have your test back yet, but maybe Thursday, I don't know. I'm sort of, it feels early for this, but I feel like I've sort of hit that point where you're just like running around trying to get stuff happening as you walk from place to place or whatever.
Yep.
Hopefully I can get my feet back under me. Maybe Thanksgiving break will
That's what I
help.
was about to say. I was thinking the same thing. I'm like, no, I get it. I'm ready for my 5-day weekend for Thanksgiving break.
Yeah,
Part towards the end of the semester, which is the.
yeah. Okay, so let me just summarize super quick where we were last time, and then we'll get into some new stuff. So we're on the Rankine power cycle. And if you look at it on a temperature specific entropy graph, the ideal Rankine cycle looks like this. And the states are, so from 1 to 2, you're going through, and I'll say this in a second, but you're going through the turbine there, then you're going through the condenser to 3, then you're going through the pump to 4, and then the boiler from 4 back to 1. And so it's going around this loop clockwise, and by it I mean the working fluid, which is almost always water. You have the turbine from, so this is state 1 going into the turbine, 2 coming out of the turbine. Then you have the condenser going from 2 to 3. And then you have the pump going from 3 to 4. And then you have the boiler going from 4 back to 1. So what do we know about these different things? From state 1 to state 2, for the ideal Rankine cycle, we have an isentropic turbine. You can see that on the TS graph, going from 1 to 2, that specific entropy stays constant the whole way. And this is where the work is done. I'll call that W sub T. And we're going from state 1 to state 2. And mathematically, what we know about this is that the rate of work done by the turbine divided by the rate of mass flow is equal to the entropy at state 1 minus the entropy at state 2. Oh, one quick question. Where do these, so I'm going to give you all these relationships for the work rates and the heat rates. What equation do these all come from? How did we derive all these?
That was the control volume.
First law and control volumes. Yep, all these come from first law for control volumes. And then second, from states 2 to 3, we go through the condenser. That's constant pressure. You know the fancy word for constant pressure? I don't think I've mentioned this, but Isobaric.
Isobaric.
It doesn't count if you say it after I say it.
Yeah. After you said it, I'm like, oh, I get that.
Yeah.
Now I remember.
And so I'm just going to keep drawing these in the orientation from the figure above. So in this case, we're going along the bottom through the condenser from state 2 on the right to state 3 on the left. In the condenser, heat is coming out. That's why you get flipped order of the enthalpy values compared to the boiler. Otherwise, it's the same equation, but so Q dot for the condenser divided by M dot is equal to H2 minus H3. And then from 3 to 4, we have the pump. This one is also isentropic. Oh, isobaric, you can remember that because like barometric, Isentropic pump. So this one's going like up the left side of my figure. From state 3 at the bottom to state 4 at the top. And you get that the work going into the pump divided by M dot is equal to H4 minus H3. So first, notice that the order of the enthalpies is switched compared to the work of the turbine. That's because the sign convention is opposite for the turbine and the pump. And then also the second thing is we have another way to calculate this rate of work in divided by the mass flow rate for the pump. That is V3 times the quantity P4 minus P3. Anybody remember how we derived that formula for that second formula for W dot over M dot?
And the relation between enthalpy and the energy and work.
Yeah, we use the TDS equation. It was isentropic, so we could simplify it. And then the second thing that we substituted in was that pump. Remember, this is always a liquid the whole time. So you're going from a saturated liquid to a compressed liquid, and so you can assume that it's incompressible.
Yep, so the same volume, so just V3.
Right.
Gotcha.
And then the last one, state 4 to state 1. This is, again, isobaric. It's the boiler. And we have compressed liquid going into the boiler from the left in this picture. That's state 4. And we have saturated vapor coming out at state 1 on the right in my figure. And the equation for Q dot over M dot is H1 minus H4. And again, you just have it flipped compared to the condenser because what we're calling a positive heat transfer is opposite in those two cases. We're calling it positive if heat's being added to the working fluid in the boiler and if heat's being taken out of the working fluid in the condenser. So before I go into sort of a long problem, I want to say a little bit about the condenser. So there's sort of two flows of key fluids in the condenser. Okay, so this is the condenser. We know that the working fluid is going this way from our state 2 to our state 3. So this is the working fluid, almost always water, but it doesn't have to be. And it has constant pressure. But then there's something else going on too. There is also water going into the, like flowing against this working fluid that's taking the heat from the working fluid. This is the cooling water. And this is always liquid. And since it's always liquid, it's a reasonable assumption to consider it incompressible. So in a simplified case, which is what we're always going to use unless, you're told differently by the problem. All of the rate of heat transfer, all this QC dot goes from the working fluid to the cooling water. And so a lot of times, if you ever get asked anything about what's happening with the cooling water, so let's say to include the cooling water in calculations, treat the entire condenser as a control volume. Assume there's no heat transfer into or out of the control volume. And treat the cooling water as incompressible. Okay, so I said this kind of fast, but why does it make sense to assume that there's no, so if we treat the entire condenser as as a control volume, why does it make sense to assume that there's no heat transfer? The whole point of the condenser is that heat is transferred out of the working fluid. So why does that make sense? Do you sort of follow that?
It's only being transferred into the
cooling fluid? Exactly. Because now the cooling fluid is part of our system. It wasn't before. And all of the heat is going into then another part of our control volume. Okay.
Yeah, you lose way more heat to that water than you probably lose to air regardless.
Yeah, that's the idea.
Okay.
Okay, so let me do sort of a quick example of how you would do something like this. So let's say the working fluid enters a steady state condenser as a mixture of liquid and vapor at saturation. So let's say that the quality is 0.6. And the pressure is 0.2 bar. And the mass flow rate of the working fluid is 4.0 kilograms per second. And now let's say the cooling water has a mass flow rate of 20 kilograms per second. Enters the condenser at 10 degrees Celsius. And we want to know what is the final temperature of the cooling water. You know, the exit, let's say, the exit temperature of the cooling water. It looks like I didn't give a lot of information about the working fluid. I didn't really say anything about what's happening at the exit, but this is the kind of thing that you have to get used to doing for the Rankine cycle. We do know a lot about it because the condenser is constant pressure, so we know that the final pressure is 0.2 bar, okay? And if you go up here to the TS diagram of the ideal Rankine cycle, the condenser is 2 to 3, and so you know that you come through the condenser as a saturated liquid, okay? So you know that that pressure is enough to look up any values, okay? All right, well, so here's we're going to use the control volume first law. So d dt is equal to q dot minus w dot plus m dot of the working fluid times, I'm going to replace the inlet and outlet on this with the state numbers that we're used to using. So it's coming in at state 2 and leaving at state 3. So the quantity here is H2 plus V2 squared over 2 plus GZ2. And then at the exit, we have the mass flow rate of the working fluid times the quantity H3 plus V3 squared over 2 plus GZ3. And now we have to consider since our control volume includes the cooling water that's in the condenser, we have to consider that. So now we also have plus m dot of the cooling water times, so I'm going to call these the inlet and exit for the cooling water. So this is HI plus VI squared over 2 plus GZI, and then minus what's happening at the exit of the cooling water. So m dot for the cooling water times the quantity HE plus VE squared over 2 plus GZE. And now a million things cancel. Steady state, so that goes away. We're assuming no heat transfer. We're assuming no work done because it's just a rigid device. We'll cancel all the energy terms. I didn't say that, but you'll always do that unless you're told otherwise. And so you come up with this equation. You can see all we have left are the m dots and the h's. And you can arrange this into a form m dot for the cooling water times h exit minus h inlet. So that's all that's left representing the cooling water, is equal to the mass flow rate for the working fluid times the quantity H2 minus H3. The mass flow rate of the cooling water is 20. Mass flow rate for the working fluid is 4. I think that's what I said, right? Okay, so we have HE minus HI is equal to 0.2 times the quantity H2 minus H3. Just substituted in the mass flow rates. So now this depends on these 4 enthalpies. Do we have enough information to look those up? Well, we do have enough information to look up the ones for the working fluid. And for the cooling water, since it's incompressible, we can actually just calculate those using the incompressible assumption. Okay, we can calculate that change. Okay, so H2, what's the state of the liquid at state 2?
Wait, no, it's not saturated, it's mixed phase.
It's mixed, yep. So state 2, we have quality of 0.6 and a pressure of 0.2 bar. So H2 is 0.6 times the enthalpy of a saturated vapor at 0.2 bar, which if you look it up is 2609.7 times 10 to the third. And then plus 1 minus 0.6, so 0.4, times the enthalpy for a saturated vapor at that pressure. And if you look it up, it's 251.4 times 10 to the third. And this gives you a value for the enthalpy at state 2 of 1666 times 10 to the third. State 3, what's the phase what's the situation for saturated liquid? That's right. So, and it's still at that same pressure that it was at state 2, so we can just use this value that we looked up for the saturated liquid, 251.4 times 10 to the third. Okay, so what about the cooling water? Well, we could look it up if we could look it up in the table for water. We do have that. We could look it up. But we can also just assume that it's incompressible and do that calculation. So for incompressible, the change in H is equal to the change in specific internal energy plus the change in pressure times volume. So you can think of that as, so change in specific internal energy plus, since in our case, we have, well, let me write it as, it's incompressible, so we know that that specific volume stays the same, times the change in pressure. But this is constant pressure, so this goes away. And so we get that the change in specific enthalpy is just equal to the change in specific internal energy, which is C times the change in temperature. And for liquid water, the specific heat is about 4186 in SI units. And then the change in temperature is the temperature at the exit that we're trying to calculate minus the temperature at the inlet, 10 degrees Celsius. On that. And so go back to this equation. This HE minus HI is just that change in enthalpy that we just came up with an expression for. So we have that 4186 times the quantity TE minus 10 is equal to 0.2 times the quantity 1666 times 10 to the third minus 251.4 times 10 to the third. And so the temperature of the cooling water at the exit is 0.2 divided by 4186 times the quantity 1666 times 10 to the third minus 251.4 times 10 to the third plus 10. And so the temperature of the cooling water at the exit is 77.6 degrees Celsius. Any questions about that? Okay, so now I'm going to get into just a long example problem. It just has a lot of parts and stuff. And when we're done with this long example problem, you'll be like, oh, yay, we're done. But then I'm going to talk about how to incorporate irreversibilities into this stuff. And we're going to do the same example problem again with some with some known irreversibilities, so you can see how inefficiencies in the system get built into the calculations. Okay. Okay, so hold on. Okay, so we have an ideal Rankine cycle. That uses steam as the working fluid. Saturated vapor enters the turbine. At 8.0 megapascals. And saturated liquid exits the condenser. So it's not exiting the turbine, it's exiting the condenser. At a pressure of 0.008 megapascals. Okay, so that's the first bit of information. That's a super low, like basically 0.01 megapascals of pressure. That's a really low pressure. That's about 1/10 of atmospheric pressure. Why would you want the condenser pressure to be that low? Is there any reason? It would take effort to make it that low. Well, we didn't do a calculation on this when we did it for temperature last time, but I did mention that the overall efficiency of this cycle increases as the pressure in the boiler goes up and as the pressure in the condenser goes down. Same with the temperatures.
Yeah.
So it's in your interest to try to get the boiler pressure high and the condenser temperature pressure low. Okay, the net pressure, net power output of this whole cycle is 100 megawatts. And what we want to know is the following million things: the thermal efficiency, the back work ratio, the mass flow rate, the rate of heat coming in at the boiler, so I'll call this sub B. So Q dot sub B. The heat transfer out at the condenser, so Q dot sub C. And finally, the mass flow rate of the cooling water given that the temperature at the inlet coming in is 15 degrees Celsius and the temperature going out at the exit is 35 degrees Celsius. When you look at the stuff we're given, it's kind of amazing that that with that little information, we can calculate all this stuff. But remember that with these ideal Rankine cycle calculations, there are a million assumptions that we're making about what's saturated, what's whatever, what's isentropic. And all of those are going to let us fill in what look like gaps in what we know. Okay, so let me see. So there's the question. Let me sort of write these out as, so there's state 1, state 2, state 3, and state 4. Okay, and I'm just going to fill in the stuff that we're given and the stuff that we know based on assumptions. Between 1 and 2, that's the turbine. Between 2 and 3, that's the condenser. Between 3 and 4, that is the pump. And then 4 and 1, I guess I'll write it over here, that's the boiler. Okay, so going into the turbine, we know we have a pressure 1 of 8 megapascals. Above this, let me write, I'm just going to squeeze this in. We know that this is a saturated vapor going into the turbine. So since it's a saturated vapor and we know the pressure, we can look anything up that we need. And I'm going to call this S1. Let's say we know this. I haven't looked it up yet. Well, maybe I should just, well, I'll do that in a second. Okay, we know that because we can look it up. What do we know? What's the other stuff we know? We know coming out of the condenser, we knew it had that low pressure, right? So P3 is 0.008 megapascals.
We know it's a saturated liquid too.
Yes. This is like my nightmare, like trying to do like GRE logic problems in front of everybody up at the board. Okay, so we know it's a saturated liquid. We know P3 is 0.008 MPa. Well, that means we know that at state 2, so this is a saturated mixture, right? And we know that S2 is equal to S1. Because that turbine is isentropic. And we also know that P2, since the condenser is constant pressure, P2 is equal to 0.008 megapascals. And then 4, what do we know about state 4? We know that that is a compressed liquid.
Let's know the power output.
Yeah, so we'll get to that in a second, I guess. We know it's a compressed liquid. We also know that since the boiler is constant pressure, we know that the pressure P4 is 8 megapascals. So we have everything we need to look up states 1 and 3. You know, we can use the table here and here. And then from there, I guess let's look those up and we'll have to find the other stuff. If we're trying to find the thermal efficiency, remember our goal is that we have this expression. I hope I have it written down somewhere.
That's going to be the QC at the condenser and then the QB at the boiler for getting our thermal efficiency.
Well, the way I was thinking about it was
Or always work output.
we want this. So remember, we have that expression that says down anywhere, but we can calculate it, I guess. So this is, we know that this is equal to Q dot for the turbine over M dot minus, no, not Q, W, minus W dot for the pump over M dot divided by,
Work in the pump too, on top of getting work out from the turbine.
yeah, that's right. So you're using some of that energy from the turbine to power the pump. And if it takes more to power the pump than you're getting out of the turbine, then your plant is useless, you know. And we're dividing by the heat at the boiler divided by M dot. And so we have the expression so WT, so this is H1 minus H2 minus for the pump H4 minus H3 divided by the heat at the boiler, H1 minus H4 and so you can rewrite this H1 minus H4 minus the quantity H2 minus H3 divided by H1 minus H4. And you get 1 minus H2 minus H3 over H1 minus H4. Well, that's something. Is that the expression that I had before? Look. It is? Okay. So that's what we're trying to come up with. And so so in order to get that thermal efficiency, what we'd like is to have the enthalpies at every one of these states. We already know we can look up the enthalpies at two of those states. Okay, so let's look up the ones that we can. So for state 1, that's a saturated vapor. And we have a pressure of so H1 is equal to 2758 times 10 to the third. And also, since the process from state 1 to state 2 is isentropic, it'll be helpful to know the entropy at state 1, because then we can then we know that that's the entropy in state 2 also, and we can use that to calculate the quality. Are you with me on that? Because we know that at state 2, it's a mixture. We know that it's at saturation. And so once we calculate what the quality is, we can use that in the table to calculate the enthalpy at state 2. Okay, so S1, we'll look that up, and it's 5.7432 times 10 to the third. Okay, so now let's go to state 2. State 2 is a saturated mixture. We know that the specific entropy at state 2 is equal to the specific entropy at state 1, and that is 5.7432 times 10 to the third. So now, since we know the pressure at state 2, we can use the saturation table for 0.008 megapascals, and we get that 5.732 times 10 to the third is equal to X times the specific entropy for a saturated vapor from the table, which is 8.2287 times 10 to the third, plus the quantity 1 minus X times the specific entropy for a saturated liquid at that pressure. So that's 0.5926 times 10 to the third. And that lets us calculate that quality. So X is equal to 0.6745. And now that we know the quality, we can calculate the specific enthalpy. That's equal to 0.6745 times the specific enthalpy at saturation for a vapor at that pressure, 2577 times 10 to the third, plus 1 minus that is 0.3255 times the specific enthalpy for a saturated liquid at that pressure, which is 173.88 times 10 to the third. And so H2 is 1795 times 10 to the third. Okay, so we have the specific enthalpy at state 1 and state 2. We're on our way. At state 3, we can look this up. We know it's a saturated liquid. We know the pressure. If we didn't have information there, remember there's another way to go for the, oh no, it's the, well, yeah. So we can look it up for state 3. Remember that when you're on state 3 and state 4, if you can't look stuff up, be aware that you have that other way of doing a calculation based on the fact that it's incompressible. But let's just look it up for state 3. So this is a saturated liquid. And H3, and we know the pressure. What was the pressure? It was that low one, right?
Yeah, 0.008 MPa.
Okay, so P3 is 0.008 MPa. And so H, so we can just use the table. And so H3 is 173.88 times 10 to the third. And then the last one is state 4.
Wait, so H2 and H3 are the same?
No. So we use the, right. We did use the same one because the pressure was the same and they're both at saturation, but we had to use the quality to get it for state 2, and for state 3 it was all liquid.
Yeah.
Okay, so state 4 now, this is the compressed liquid. And so we don't have enough information yet, at least, to look it up in the table. We do know the pressure is 8 megapascals. We don't know anything about the temperature. I don't see a way that we're going to look this up in the table. So let's think if we can use the incompressible assumption. So we know that H4 minus H3 which is equal to the work rate of the pump divided by the mass flow rate, is equal to the specific volume at 3 times the change in the pressures And so H4, if we rearrange this, is equal to the specific volume of liquid water is about 1 times 10 to the minus third. The pressure at 4 is 8 megapascals, so 8 times 10 to the 6. The pressure at state 3 is 0.008 times 10 to the 6. And then you have to add on that specific entropy at state 3. And we have everything here. So H4 is 181,872. The what? That is the specific, that came from my brain, but you can look that up at different temperatures.
Just doesn't vary much.
It doesn't vary very much. It's just, yeah, you know, that's just because the density of water doesn't change very much.
I assume that's just at SPP.
You could look up, that is it, yes, that is it, like atmospheric pressure, standard room temperature. But you could, if you want to be really careful about it, you know the two states, like you know the pressures at the two states, and you know that the specific volume of an incompressible liquid only depends at all on the temperature. So you can look up the corresponding temperatures at saturation and then use that to look up the specific volume. But it would be very close to that no matter what. Okay, so there's H4. And so now we have the specific enthalpies at each of those 4 states. And our thermal efficiency is 1 minus whatever I just said before. H2 minus H3 over H1 minus H4, was it? Okay. And so that's 1 minus the quantity, 1795 times 10 to the third minus 174 times 10 to the third divided by the quantity 2758 times 10 to the third minus 182 times 10 to the third, and you get 0.371. Yeah, that's A. Maybe it'll be easier now though, because we have a lot of stuff that, like for example, the back work rate is also just calculated from enthalpies. So at least for a couple now, we get to just plug in stuff we already found. I will try very hard on tests not to make it feel like just a, you know, but on homework, you might just have to do some of this stuff.
If all is fair there.
Yeah, exactly. Okay, so the back work rate, that is the rate of work done by the pump, or done to the pump over the mass flow rate divided by the work rate at the turbine divided by the mass flow rate. And that is H4 minus H3 divided by H1 minus H2. And that's 182. I'm going to just divide out all the times 10 to the thirds. Minus 174 over the quantity 2758 minus 1795. And so the back work rate is equal to 8.31 times 10 to the minus third. Oh, let's think for a second about what these mean. So first of all, is this, how about for the thermal efficiency, is 371 good? It's a good baseball batting average.
Okay. I think it's okay.
So what it means is, it means the fraction of the energy that you're putting in as heat at the boiler that comes out as work, useful work. You'd like it to be 1, but I think this is in the ballpark of what you're going to get.
Yeah, I was going to say that's probably a typical value.
I think that is a pretty typical value. And then the back work rate. Now this is the rate of work required to run the pump divided by the rate of work that you're getting from the turbine. You want this to be really small, and apparently usually it is really small. So I don't know, that looks pretty small. That's as much as I know about it. You don't want that to be 100%.
Yeah, doing a ton of work just to compress it.
Yeah.
There's one thing about the ratio of the pressures. I know for the isentropic pump, I'm looking at the work power.
Mm-hmm.
The second equation where we have a specific volume P4 minus P3.
Yeah.
Wouldn't you want P3 to be larger, not smaller?
Okay, say it again. This is the isentropic what?
The pump. Because we have the work done on the pump over the mass flow rate is equal to the specific.
Oh, so you're going back to the control volume thing?
Yeah.
Yes. Okay, here's why it works that way, because remember that we change our sign convention for the work.
Okay, so then we do want P3 to be large in this case.
We want, well, let me see what it says. Maybe I did write it wrong.
I'm mostly just thinking about the ratio of, the pressure going into the boiler.
P4, so the condenser is P3 to P4?
Yep.
Yeah, you want P4 higher for sure.
Yeah.
So do I have it backwards? The whole point of that pump is to increase the pressure at P4 compared to P3.
Okay, yeah.
So you want that?
Yeah, P4 is the 8.
Yeah. Okay. So I think that makes sense. Yeah, you want it to be this.
Right here,
yep.
You want P3 to be larger, so less work is done.
Well, you might want it in this case, but
when you go through the entire thing.
But I mean, what you have to do, the whole point, like what you're trying to accomplish with that pump, is to get low pressure working fluid into the high pressure boiler,
Yeah.
And so.
I should say, smaller P3 here will require more work out of the pump, but we still, because we have that other.
Yes.
Right. What was that relationship? You want P3 to be smaller though? Is that
yes.
Because coming out of the turbine, or I should say not turbine?
Yes. Yeah. Out of the condenser.
Oh yeah.
Yeah. You want a low pressure at the condenser. Yeah.
Okay.
Not for this, but for not because it will, like you said, that's not good for the work that's required from the pump, but it's good for the overall efficiency of the
work coming out of the turbine, I assume.
Just for we did that whole calculation of the thermal efficiency based on pressures. Well, I didn't do it, I just implied it. I did it for the temperatures.
Yeah.
And through that calculation, what you would see is that
when you have that smaller P3, you do end up having a better thermal efficiency.
Yes, exactly, exactly. Okay, so now we're on to part C. Mass flow rate of the steam. Okay, so now we're trying to calculate m dot. And we know that the work dot done by the turbine minus the work dot that's required from the pump is equal to 100 megawatts, so 100 times 10 to the 6. And so we can write, work dot at the turbine divided by m dot is equal to H1 minus H2, which is 2758 times 10 to the third minus 1795 times 10 to the third, which is 963 times 10 to the third. So right now I'm just using the equations that were like in my summary at the beginning of class today. The work rate required by the pump divided by m dot is equal to H4 minus H3. And that's 181,872 minus 173,880. Again, we're just plugging in stuff we'd already figured out, and so that's 7.99 times 10 to the third. And so 100 times 10 to the 6, that's the 100 megawatts, is equal to m dot times the quantity 963 times 10 to the third minus 7.99 times 10 to the third. And now you can just calculate m dot. And so the mass flow rate is equal to 104.7 kilograms per second. Okay, so now it asks, I guess, the next couple are a couple of questions about the rate of heat transfer. So the next two are the rates of heat transfer at the boiler and the condenser. Well, now we have the mass flow rate. So we know that W dot at the turbine divided by m dot is equal to H1 minus H2 and so we know that W dot at the turbine is equal to the mass flow rate times the quantity H1 minus H2. We know all those things. And so W sub T dot is that what I'm looking for? I'm doing the wrong thing.
I think it's the heat.
Yeah, I want the heat. it's the same kind of approach as that, but so we want the heat at the boiler. Sorry about this. Heat at the boiler is H1 minus H4 and so Q dot at the boiler is 270 times 10 to the 6th, so 270 megawatts. And then we want to do the same thing at the condenser. So QC dot is equal to M dot times the quantity H2 minus H3, which is 104.7 times the quantity 1795 times 10 to the third minus 173.88 times 10 to the third. And so QC dot is equal to 170 times 10 to the 6th. And then the last one, we're looking for the mass flow rate of the cooling water. So this one we have to use the approach that we did right before we started this example problem. We're going to use the control volume for the whole condenser, including all the liquid coming in and going out. And then we'll come up with an equation for M dot. So we have dE dt is equal to Q dot minus W dot plus the mass of the cooling water, the rate of mass flow of the cooling water, times, we're canceling everything except the enthalpies, so I'm just going to skip ahead. So we have H for the cooling water coming in at the inlet, minus H for the cooling water going out at the exit. And then we have plus M dot for the working fluid times the quantity. This is for the condenser, so we have H2 minus H3. It's steady state, no heat transfer except exchanging between those two liquids, no work. And so you can rearrange this equation to say M dot for the cooling water is equal to the quantity H2 minus H3 divided by H for the cooling water at the exit, minus H for the cooling water at the inlet.
Shouldn't that be the other way around? Or oh wait, yeah, never mind.
You have to, yeah, you get them to the opposite sides of the equation, and so I think that's right.
Okay.
And so now it's incompressible. So the cooling water is incompressible. And I'm missing M, aren't I?
Yeah.
M is on top, isn't it? Thank you. I got sick of working on this and didn't finish, sorry. Okay, so the cooling water is incompressible and the pressure is constant from the inlet to the exit. So the change in enthalpy for the cooling water is the change in specific internal energy plus VDP, and that second term goes away. So this is 4186 times the quantity, final temperature minus initial temperature. And those were given. 35 minus 15. So M dot for the cooling water is equal to M dot for the working fluid, which was 104.7, is that right? Yes, 104.7 times H2 which was 1795 times 10 to the third minus H3, which was 173.9 times 10 to the third, divided by 41,860. Oh, no, that's 20, not 10. So 2 times that. So 83,007. Thank you. And M dot for the cooling water. Can someone punch that in for me?
I got 2027.4. We'll got the same.
2027.4 kilograms per second.
Get a different value? No.
Okay, yay. Okay, well, that is definitely enough of that problem. Except that, like I said, we're about to do it all again.
Yep.
But so you all might want to cancel whatever you have scheduled for the rest of the afternoon. No, just kidding. But the good thing is, so what we're going to see next is the way that we're going to incorporate irreversibilities into this stuff is sort of as a correction factor. So really it's not going to be like this again. We're going to take these values we already figured out and use sort of a correction on it. So actually figuring out these values again for the more inefficient cycle is going to be really fast now that we've already done all this. Okay, that's all.